Assalamu alaikum everyone. Last time we discussed about the different excitation techniques which are used for powering up the field winding of the synchronous generator. Then we moved towards the modeling of the synchronous generator. Essentially, we wanted to know, okay, how can we calculate the output voltage and output frequency of the synchronous generator. So on that route, we defined that the electrical frequency of the synchronous generator can be calculated by this formula, which is the mechanical speed times the number of poles divided by 120. And we also discussed about the open circuit curve, which is essentially the magnetization curve, and we said that the open circuit output voltage, which is represented by EA, is given as K phi omega, where phi is the flux in the machine and omega is the speed of rotation of the prime mover, and K depends upon the machine construction, and we derived it last time that it was the number of loops in the coil and times the number of poles divided by under root 2. Okay, and this then the unit of EA is the RMS root mean square value. So this was where we were last time, and today our goal is to obtain the equivalent circuit of the synchronous generator. We'll be building on these concepts and we'll be introducing more to get the equivalent circuit. So in order to have an equivalent circuit of the synchronous generator, we need so there are essentially the four key effects that are that we need to model. So one is the armature reaction, second is the self-inductance of the armature coils, resistance of the armature coils, and fourth one is the effect of the silent poles. So since we are mainly focusing on the non-silent machines, currently we are not targeting this effect, which is the effect of the silent pole. So if you want to read about this effect, then you can refer to the appendix of the books. So let's focus on these three effects, which are the जिनको हमने essentially model करना है. So easiest one to model are the point number 2 and 3, which are the self-inductance of the armature coils and the resistance of the armature coils. We know our armature, which is on the stator of the winding. So remember we have in synchronous generator we have a stator on which we have three different sets of windings, which we have a three-phase winding, and we have one winding which is a field winding on the rotor. Okay, so if we roughly model it, then we can say कि हमारे पास we have two parts. One is the rotor part, which is just a field winding. So it will essentially have the field inductance and the field resistance. So it is the field resistance and field inductance. So let's represent that by XF. So that's our field circuit, which is on the rotor. So this is on the rotor, and if we see on the armature, we have the coils on the armature. Okay, and secondly, the voltage is also being induced on the armature. So it means that if we see only single phase, so we have we will have a replica of three all circuits. So if we see only this three single phase, we have an internal generated voltage, which is the EMF that is being generated. That is basically your EA, which will be coming from the open circuit curve. So इसकी expression we saw it, the EA is K phi omega, and we just saw what the K is. And so each coil has the resistance of its own. So that simply will be modeled as RA, which is the resistor, and each coil has the self-inductance because it's a coil. so it means it has the inductance, self inductance as well. Okay, so that is XA component. Okay, JXA. So now so these two are very easy, and we know how to model those. So the one thing that we need to consider is the armature reaction. So that's very interesting part. So I would suggest to pay attention to this one. So as we know what armature reaction is, when so armature reaction is the distortion of the flux in the machine when there is a load connected to the machine, right? So we discussed that into the DC machines as well. So what happens here is when there is no load connected here in this machine, so it means there is no armature reaction. उस केस के अंदर हम we do not have to worry about the this term, ठीक है, when there is no load. But when we connect a load to this machine, it means when we connect something like a resistor or inductive load, the lagging load, if we connect this one, so it means there will be a current flowing into this branch, and this means there will be a current flowing in these coils, and now that current is essentially the load current, and that current will generate its own magnetic field. So and now that magnetic field which is basically, so let me show you one more figure. So for example, there are 4 figures, so let's focus on figure A, which also essentially only shows कि आपके पास you have a rotating magnetic field, you have a rotor which is generating the rotating magnetic field, and on the armature you have a 3-phase windings जिनके अंदर आपका voltage induce हो रहा होगा. And so one thing that we observed that the voltage induced will be the sinusoidal into these coils, so it will be a sinusoidal waveform. So where will be this peak of the sinusoid? So the peak will be appearing wherever this field is pointing to. This we observed in the DC machines as well. Okay, so wherever this vector is, so the general observation was whichever conductor is cutting the magnetic field line, so that will have a more voltage induced in that conductor as compared to other conductors. So it means जो हमारे पास peak voltage होगा, that will be along this plane. ठीक है, इट मीन्स के ये जो वाइंडिंग का सेट है इसके अंदर देयर विल बी अ पीक वोल्टेज. ठीक है, सो नाउ if we connect a load to this winding, this 3-phase winding, it means that there will be a current flowing into the machine, and so for example we connect a resistive load. So the simple case, we connect a resistive load, it means the current will be flowing which will be in phase with this waveform. Okay, so it will be in phase with the voltage waveform if we connect just the resistive load. So if we have that current, it means this current will, so now whatever this current is flowing is, so that component of the current will generate its own magnetic field, right? कि आपके पास so for example it will follow this dot and cross convention. It means if we apply the right hand rule, so it means this will generate a magnetic field of its own. So this is the magnetic field vector. So if you apply the right hand rule, if you curl your right hand fingers in the direction, so this is coming out, this point is coming out, and this is coming in. So if you curl in this direction, so you'll see your thumb will be pointing in this direction. It means this vector, this load current is producing its own rotating magnetic field vector, so that will be lagging 90 degrees behind the actual rotating magnetic field. Okay, so now what will happen is that this vector, again this is also a magnetic field, so this is, let's call this BS, the magnetic field which is produced because of the stator. and this is the magnetic field which was present in the rotor in the first place. So this is due to the current flowing in the stator, and that will so once we have this vector, it will generate it will induce an EMF into the coils. So because it's, of course, it's also rotating. So think about it. You have two vectors connected end to end, and those are rotating now. So now this will be this vector will also be inducing the voltage. So it means if you see the terminal voltage, which we, let's suppose, represent by the V phase, so that will be equal to the EA voltage, which was the voltage that was produced only due to the rotor magnetic field, plus the E stator voltage. So that's the voltage that is being induced because of the armature reaction, or in other words, that's because of the load current that is flowing in the stator. So that current produces the magnetic field, and magnetic field induces the voltage into the same coil. Okay, so that's what the armature reaction is. It means it will generate this voltage as well. So we need to we already know how to find out how to get this EA is obtained from this equation, which was this one. EA is K phi omega, and we'll get the value of EA from open circuit curve. So that's easy, that's done. And let's think about how can we model the ES, which is the voltage that is being generated because of the armature reaction. So one thing that we know from here, जो अभी जिस तरीके से हमने इसको डिस्कस किया एंड डिस्क्राइब किया कि how it is generated. So one thing that we know कि ES is basically proportional to the IA, your load current, whatever the load current that's flowing there. The more current you have, the more strength of the stator magnetic field vector will be generated, and will induce the more component, more stator component, which is the armature reaction component into the voltage. So it means it's proportional to the IA. And one thing more that we know that it is lagging the rotor magnetic field. So it means the voltage that will be induced will be lagging the EA as well. So it means so ES should have the component of lagging minus 90 degree, which is minus JIA. Okay? And if we see we can place any proportionality constant, which we call X, or in other words, the armature reaction reactance. Okay? So X is the armature reaction reactance. Okay? That's just a constant to model that effect, the proportionality constant. Okay, so we got that. Okay, how to model this armature reaction. So let me show you so that was a very simple example. So let me show you more complicated one, which is shown in this figure as well. So it's nothing but another way of saying so we assume कि हमारे पास जो current flow हो रहा है, that is flowing in phase with the EA. So that's not always the case. This is only the case when you have a resistive load, purely resistive load. But if you have an inductive load, then the current that will be flowing will be lagging behind the EA. As we know, if you have an inductive load, current lags behind the voltage. Okay, so that's obvious. So it means again, so there's the same idea if the current lags behind, then we can apply the right hand rule to this plane, and you can see the magnetic field, the stator magnetic field, which is produced by this current, that will be pointing in this direction. So it means in that case, so in that case, so you still have that the component which is the minus JXA component. Okay? So that is being modeled by the armature reaction. Okay, so let's summarize all this discussion. If we want to get the equivalent circuit of our synchronous generator. So the equivalent circuit will essentially look like we have a rotor side, which is just a electromagnet modeled by the resistor, field resistor, and field reactance, field coil. Okay, and on the rotor, on the stator side, we have, so this is stator, we have three coils. So last slide में हमने just एक coil को दिखाया था. So we have basically three coils now. So each coil will be 120 degree. It will have a phase difference of 120 degree with the other, right? So and each will have a resistive component. And now because we have the two reactances in the circuit. So let's see the previous slide. So we had the one reactance, which is the self reactance, which is JXA, and because of this reactance we'll add one more reactance here, which is just the JX. Okay, so we can combine these two reactances and we can call this reactance as the synchronous reactance, which is represented by XS, which is basically the sum of the reactance due to the armature reaction and the self reactance of the armature coils. So that is combined into one parameter, which is the synchronous reactance. Okay, so basically we got our three phase the equivalent circuit of the synchronous generator. Okay, so now we can when we have the three phase windings, which are I'm talking about these output windings. So now you can essentially you want to supply the three phase voltage to the output, to the whether you want to supply to the consumer or someone else. So you essentially will you can connect the three phase windings. So you can essentially give each phase individually, but generally three phase windings are connected into the Y or the delta fashion, as you know. Okay, so it means you can connect these three phase connections into the Y connection. So in that case the line voltage will be the under 3 times V phase, and the line current will be the same as the phase current. And you can also connect these three phase connections into the delta connections, and in that case V terminal voltage will be equal to the phase voltage, and line current will be under 3 times the phase current. Okay, so that we have already studied into our transformers, how to analyze the three phase, how to construct the equivalent circuits with the three phase circuits, and how to analyze those. So we'll apply the same techniques here as well. Okay, so let's do an example now. So very good example. It will give you an idea कि अभी तक जो हमने सीखा है उसको हम किस तरीके से अप्लाई कर सकते हैं. So let's see, we have a 480 volts 60 hertz delta connected 4 pole synchronous generator. So let's write P is equal to 4, F electrical is equal to 60. Has the open circuit curve, which is shown here, which is 5.23 5-23A. This is the figure. This generator has the reactance of 0.1 ohms and synchronous reactance of 0.1 ohm. It means it is XS is equal to 0.1 ohms, जो भी हमने last slide में discuss किया था, and armature resistance, which is RA, which will be 0.015 ohms. So remember, these parameters are phase parameters. So in each phase we have a synchronous reactance of 0.1 ohms, and in each phase we have an armature resistance of 0.015 ohms. So at full load the machine supplies 1200 amperes and 0.8 power factor lagging. Under the full load conditions, the friction and the windage losses are 40 kilowatts, core losses are 30 kilowatts. Ignore any field losses. Okay, so let's see what's being asked. So first is, what is the speed of the rotation of this generator? Very easy. So we know Fe is related to the mechanical speed by this formula. So we can rearrange this equation and we'll get Nm is equal to 120
times the frequency, which is the 60 hertz, divided by poles, which is the 4. If you substitute this expression, you'll get 1800 rpm. Okay, so let's see in the second question, how much field current must be supplied to the generator to make the terminal voltage 480 volts. So let me remind you, what do we mean by the terminal voltage? We have a synchronous generator, okay, and so this is the open circuit voltage, and so this is your equivalent circuit with the RAXS, okay, and this is your V phase, okay, and this is a per phase equivalent circuit, and this is saying that we have a delta connected load. It means in delta connections, so V phase will be equal to terminal voltage, whatever the phase voltage is, and also this is because we have a no load. So we have a no load. It means ke it means ke at no load V terminal voltage is equal to EA, because there is no current there, so this current is 0 in this case, so this is EA, okay. So essentially we wanted this is asking how much field current we should supply to this machine to make the terminal voltage equal to 480 volts. In other words, we want to generate the open circuit voltage to the 480 volts. So let's see, where is the 480? So it's somewhere here. So if I plot this curve somewhere here, okay, somewhere here, so it's around 4.52 or 4.5 amperes. So let's call this as so we need field current is equal to 4.5 ampere to generate open circuit terminal voltage of 480 volts at no load, okay. So this is part B. So let's move towards the part C, which says if the generator is now connected to a load and the load draws 1200 amperes and 80.8 power factor lagging, how much field current will be required to keep the terminal voltage 480 volts? Okay, so now we have a load current as well. So only thing that is different now is now we have a current there, okay. So first thing is we are drawing the current of 1200 ampere at the load, and we are connected in delta form. So it means our phase current, in this case phase current will be equal to 1200 divided by √3, and let's incorporate let's make this into the vector form and phasor form, and let's add the power factor as well. So it means the angle would be, it's lagging, so minus cosine of 0.8. so if you solve this you will get around 632, I guess. So 1200 divided by √3, so 692.8, and angle is minus 36 minus point cosine inverse of 0.8, which gives you 36.86 degrees. So this is the current that is flowing over here, which is I phase, okay. So now we have a EA here. So what do we want is we want to keep the terminal voltage is equal to the 480 volts. So when we want to keep the terminal voltage 480 volts and we have a delta connection, so it means K V terminal is equal to V phase because of the delta connection. So now we want to know what should be EA first. First we want to know what should be EA such that V phase is equal to 480 volts. So it's very easy, we can apply the KVL. So if we apply the KVL, then we know कि हमारे पास EA would be equal to so in our case this is V, so let's write me the expression first. It's a VT or V phase plus I phase, so in phasor form, and times RA plus JXS. So this will be the our open circuit voltage. So let's substitute these values. EA will be equal to 480. So let's assume that as a reference. So angle is equal to 0 plus I phase, we know this value जो अभी हमने obtain किया, which is this value, and RA we know is 0.1 plus J and X. No, I'm sorry. So this is RA is 0.015, 0.015, and armature. So that is the armature resistance, and synchronous reactance is 0.1. Okay, so this is just a substitution. If you substitute these values, you'll get around 532 angle 5.3. So this is what you should get from this one. Okay, so 5.3 degrees. So now the next step is straightforward. Okay, what should be the field current? We know the open circuit voltage, which is 532. So it lies somewhere here. So 532 is over here, which is somewhere here. So let's 5.75, 5.7 amperes. So 5 point, so it means that the field current that will be required to generate the open circuit voltage of so field current 8 EA is equal to 532 is equal to 5.7 amperes. So it means when we added the load on the machine, our field current increased from 4.5 to 5.7 ampere. So that's the conclusion of part C. Okay, so we have one more part, which is how much power is the generator now supplying and how much power is supplied to the generator by the prime mover, right? So, and what is the machine's overall efficiency? So we have a synchronous generator, we have a Pin and we have a Pout. We want to find out both these terms, what is Pin, what is Pout. And so Pout is very easy. We know Pout in our case, because we have 3-phase windings, it is V under 3 V terminal I load times the power factor. So we know कि हमारे पास in the case of the load condition, so this is referring to the part C. So in part C we have a terminal voltage of 480 volts. 532 was the internal generated voltage, so the terminal voltage is 480 volts, and load current was 1200 amperes. So that was the load current, and power factor is 0.8. So if we solve this, substitute these values, 3 times 480 times 1200 times 0.8, you have around 798.129 kilowatts. Okay, so that's our P output voltage. So let's think about how can we calculate the P input. So we do not have the input power straight away available from the mechanical side, so we can calculate the P input by calculating the P output. We have a P output, and in incorporating all the losses are given here, which is the friction losses, windage losses, and the core losses, which are 40 kilowatts and 30 kilowatts, which are the 70 kilowatts. So these are the losses, the mechanical losses and the core losses. So one losses that we need to calculate though are the electrical losses. So we need to add the electrical losses here, P electrical. ठीक है. So what are the electrical losses? Are the losses जो आपके पास equivalent circuit के अंदर resistor में आपके losses हो रहे. So those are your electrical losses. So whatever the losses are happening here, which is essentially, and this is saying कि ignore the field circuit losses. So there were the field circuit losses as well, but it's saying कि ignore that. So it means कि we know कि हमारे पास यहाँ से current कितना जा रहा है, which is that was 1200 divided by under root 3. So that's the per phase current जो हमारे पास इस branch में से जा रहा है. So that square times RA will give you the losses. So 1200 divided by root 3 IA square. So that is I times R square. So which is IRA square. So RA we know it is equal to 0.015. So these are the losses in a single phase. If we have a 3 phases, so it means multiplied by 3. Okay. So this will be the losses. So RA, so in this expression RA will be equal to 0.015, which is this one. So if you substitute this, you'll get the electrical losses of 21.6 kilowatts. Okay, so this whole thing is 21.6 kilowatts. So now we have all these things available. It means if we can sum these all up, and we'll get 889.6 kilowatts. So that is our P input. So now easily we can calculate the efficiency, which is P output divided by P input times 100. So if you substitute these values, you'll get 89.75%. So this is your P output, and P input is this value. So that's your efficiency of the machine, synchronous generator. Okay, so let's see, we have one more part on that. Yes, so one more part is it's asking is, if the generator's load were suddenly disconnected from the line, what would happen to its terminal voltage? That's very interesting part. So I'll keep that part to discuss in our question and answer session when we'll have a question and answer session on the Friday. So we'll discuss this part in our Q&A. So I'll suggest all of you to think about this part, and we'll discuss this into our Q&A. We'll stop here, and I'll see you on Friday. And on Friday, in the next class, we'll discuss more about the power considerations, power output of a synchronous generator. I'll try to derive one more expression about the power output, and then we'll discuss in the next class the standalone mode of the synchronous generator. Hopefully, then we'll wind up this chapter. So if you have any questions, let me know in the chat box, and we'll discuss that in our class. Allah Hafiz.